Bienvenue à tous. Welcome everyone for this last presentation of the Nirenberg Lectures and for our second talk this week. So we have the pleasure to hear Wang today, who will speak about restriction theory and projection theorems. So Wang, when you're ready, you can share your screen.
Okay. Yeah, thank you very much for the introduction and for the invitation. It's a great honor to deliver the last general audience lecture on restriction theory and projection theorems. So in recent years, there has been some progress on both restriction theory in harmonic analysis and projection theorems in geometric measure theory. So I try to draw some like graph and connections between them. So those green boxes belong to restriction theory. I'm going to introduce them later. And those blue boxes belongs to projection theorems in geometric measure theory. There's this outlier that belongs to dynamics. And those links between them. So the pink means that it proves the sharp estimate we want. And then the light purple means that, well, it contributes to, so it is a key input to the argument, but we don't, does not automatically give us the sharp estimate yet. As you can see, there are many boxes. Today, I will focus on Stein's restriction conjecture, which is the central open problem in restriction theory, and also a bit of Kakeya conjecture that Josh and I have been talking this week, and also and I will introduce what is Bouguin diameter decoupling. That's an important tool, and for projection theorems, I will try to discuss what is restricted projection theorems and how the Kakeya set conjecture can be viewed as a special case of restricted projection theorems. And this also has some applications in very exciting homogeneous dynamics applications and also some number theory applications. So this restricted projection theorem is a pretty unknown, how to say, a territory for me, because I can some of the theorems that we proved in the last few years are like the special case of the general question we want to study, and it's not clear. There are still lots of open problems and a lot of unknown phenomena that we cannot understand yet in the restricted projection theorem. That's and before I go to discuss details, there is one common thing is that in both fields, the presence of curvature is very important.
There is a question.
Yes. What is the meaning of the lower remark? Distinguishes R and C.
Yeah. That's a great question. So this Bouguin's discrete sum product theorem for me is theorem that's if okay, I can just state the theorem and then you will see immediately why I distinguish R and C. So this says that if say if F is some field and A is a subset of F, a proper subset, then there's A plus A and A times A, and has to be much larger than the size of A. So size could mean the dimension or anything. So this, maybe let me see. The dimension of A. And so A plus A is, we take A1 plus A2. A1, A2 in A. Similarly, A times A. So Bourgain's projection, Bourgain's discrete sum product means that this dimension should be strictly greater than the dimension of A, as long as A is like infinite subset of the field, and also it's not the field itself. As long as the dimension of A is strictly less than the dimension of F. And this theorem, if we take F to be C and A to be R, then this is not true. But the Bourgain's discrete sum product theorem says that if F is R and A has dimension strictly less than the dimension of R, then this is true. That's what I mean, distinguish R and C. Is this clear?
Yes, thank you.
Yeah, I'm a little sorry that we run into the core of the whole topic at the beginning and might be a little technical for people. Sorry, I'm just trying to see if I can pin the video because I cannot see you. Okay, so great. So let's start. Are there any more questions? Also, like I said, today I will only be focusing on this part and this part. And for all the rest that are pretty exciting for me, we won't be able to discuss in details. But if you have any questions after the talk, I'm happy to answer. Okay, let's proceed. So first of all, let me talk about restriction theory. So this is the topic of my thesis. That's my PhD thesis that I'm quite excited about. Suppose the Fourier transform of a function f is supported on a submanifold M in Rn. What can we say about the function? So when we ask what can we say about the function, we are asking a pretty simple question. What can we say about the LP norm of the function? So if the submanifold M is like a hyperplane, then this we can't say much about it because then this integral is infinity because it has Fourier transform supported on hyperplane. So by uncertainty principle, it's like the f itself is a constant function on the line that's orthogonal to the hyperplane. So when M is a hyperplane, then this question is, we can say much about it because it's infinity anyway. So the problem becomes interesting when M is curved. So here is the example. So suppose small f is a function in n-1 dimensional space, and with capital F is the exemption operator acting on small f. So writing it out explicitly, this means the follows. So x dot product with c and c squared, and then so times fc dc. And if we write this as a parameter as y in Rn, and then we can also rewrite this extension operator. So we pretend fc equals to fy. We abuse the notation, use fy to denote fc, where y is dc squared. It can also be viewed as the Fourier transform of a function, and sigma is the uniform measure on the paraboloid. So these two things are the same depending on which way you want to view it. So such f, as you can see, has Fourier transform supported on the paraboloid. So it's cc squared. So this is the support of the Fourier transform. The reason why we care about such function is because this is the solution to the linear Schrodinger equation. So it has some connection to PDE. Even this example looks simple, but there are still a lot of things that are unknown for us. For instance, like this LP norm of f is bounded by something means that the function has to be dispersed when time goes to infinity. So this is also the reason why some people study Schrodinger equation says this is dispersive PDE. It's because the LP norm is bounded for some p. And then the second important example is the moment curve. So we can say f is a function defined on R. And then capital Fx is the extension operator of acting on f on this moment curve, t squared t cubed until t to the nth. That is the Fourier transform of x dot product with this y on this moment curve. And this function, when we are interested in the LP norm, is because it has a connection to number theory. And as we will see it, we will see the connection later via the decoupling, Bogan-Diamond decoupling. So are there any questions on the two examples? So now for the first type of example, we have Stein's restriction conjecture. So it's posed by Eli Stein in the 1960s. It says that previously I said that the LP norm is bounded for some p. Now for what p? Here is the conjecture. Based on some simple function, Stein conjecture that for p greater than 2n over n minus 1, the LP norm of the first example is bounded by some constant depending only on p and n times the LP norm of its Fourier transform. So this critical exponent 2n over n minus 1 comes from the function that equals to 1 that is constant on this truncated paraboloid. Also, another almost equivalent example is like if you have a function whose Fourier transform is supported on the unit sphere, then we also conjecture that when p greater than 2n over n minus 1, the LP norm of this function is bounded by some constant times the LP norm of its Fourier transform. And the critical exponent also comes from the function whose Fourier transform equals to 1 on the unit sphere. And Stein's restriction conjecture implies the Kakeya conjecture. How they are related is okay. So I don't think I need to introduce Kakeya conjecture since people have heard a lot of this week. But let me just say that the Kakeya set is a compact subset that contains a unit line segment in every direction, and the conjecture is that the Hausdorff dimension should equal to the dimension of the ambient space, and this is Besukovich's construction says that there exists a zero Lebesgue measure Kakeya set, so that's why people conjecture the Hausdorff dimension has to be n. How restriction conjecture implies the Kakeya conjecture is based on the wave packet decomposition discovered by Jean Bourgain in the 90s. So this is pretty interesting because it's almost says that the central object for our field is about tubes, and as we can see that tubes are like the common objects in both restriction theory and also projection theory. So I think it can be fair to say that we spent that 10 years thinking about tubes. So the wave packet decomposition says the following. In a large ball of radius r, so previously we are interested in estimating the LP norm of a function on the entire space. So it's quite natural to approximate the Euclidean space by larger and larger balls. So in a large ball of radius r, the wave packet decomposition says that there exists a set of r to the 1/2 times, so a set of tubes of radius r to the 1/2 and length r, such that one can decompose the previous function as follows. So this remember this f has Fourier transform supported on the paraboloid. And the wave packet decomposition says that such f can be decomposed into sum over wave packet ft. Each ft is a wave packet. So t is tube of radius r and length r. And each wave packet ft is essentially supported on the tube. So each of them is a tube. And its absolute value is roughly constant on t. So it means that if we take the absolute value of a single wave packet, it's supported on this tube, and its absolute value is like a constant. So it means that if we take the absolute value of the wave packet, it's like some constant times the characteristic function of the tube. But of course, ft itself has oscillation. That's why I drew this oscillation here. It means that when different wave packets they overlap, instead of their absolute value adding together, the oscillation might cause some either constructed interference or some L2 cancellation. So let me try to explain this picture again. So this f is the function that we are interested in, whose Fourier transform is supported on the paraboloid. And then wave packet decomposition says that one can visualize f by saying that, okay, f is the sum over those wave packet, right? And this wave packet has support on the tubes. So it matters how the tubes overlap. And that is why a restriction conjecture is connected to Kakeya conjecture, because even though the Kakeya conjecture says it's about line in every direction, if we look at things at small resolution, it means how like tubes intersect. That's the difficulty of the Kakeya set conjecture. And beyond the Kakeya phenomenon, meaning that how tubes in different directions can intersect, there is also a part about oscillation. So meaning that when the tubes intersect at a certain point, so the different waves, how their oscillation will have some effect on the size of f. And now let's talk about the different direction and the curvature of the support. So as you can see that there are different colors. So this is a paraboloid. And then we decompose the paraboloid into small caps of radius r to the minus a half. So those numbers are not that important. And then each cap has some color. So the purple cap corresponds to those purple tube pointing in the normal direction of the cap on the paraboloid. So the fact that f has Fourier support curved means that different caps, the normal direction are different, will correspond to the fact that the tubes point in different directions. And as we can see in the Kakeya set conjecture, tubes pointing in different directions is the how to say it, like it's the definition for Kakeya set. But as we discussed yesterday, even though in the proof it's not that important, but tubes pointing in different directions is the definition, so it's a key feature. So maybe I should pause and see if there are any questions at this point. I know if it's the first time you see wave packet decomposition, it might be somewhat hard to digest, but all you need to keep in mind is that to study those function f, one can just look at this picture and say that, okay, I only need to understand two things: how tubes in different direction intersect, and when they intersect, how does the oscillation contribute to the size of f? That's the only two questions. And we are going to answer it, or we are going to try to answer it via both geometry and analysis. So here is the analysis part. That is, there is another way to estimate the LP norm of such functions, that is Bourgain-Demeter decoupling. So what it means, sorry. This Bourgain-Demeter decoupling says that one can estimate LP norm of a function by the little L2 sum of LP norm of a simpler function f theta. What is f theta? As we can see that in the previous page, F is the sum over those wave packets, and some of them are parallel like this. We have 3 parallel purple tubes and 2 parallel red tubes. And F theta means that we sum all the parallel tubes together because the parallel tubes, they are disjoint. So it's harmless to say sum them together because they don't overlap, so their size won't increase. So that is F theta, means we add the theta means direction. So it means that we add the tubes in the same directions together. And so this is like bounding a complicated function by some simpler functions. And the LP norm is like bounded by this little L2 sum. In each of them we can calculate. And as we just said that this cannot be too large because the tubes do not overlap when they are parallel. So that is Boolean diameter decoupling. Again, there is this key exponent, the critical exponent, 2n plus 1 over n minus 1. So Boolean diameter decoupling says that for any p between 2 and this critical exponent, 2 times n plus 1 over n minus 1, the LP norm of the function is bounded by little L2 sum of the LP norm of f thetas. So where does this exponent come from? This exponent again is influenced by the curvature of the Fourier support. So previously, for Stein's restriction conjecture, we have some exponent, and this is difficult. This is different, and this one comes from some people called a streetcast estimate in PDE. So that's this is the streetcast estimate exponent for the Schrodinger equation, and this is almost sharp in the sense that when p is greater than this exponent, this is no longer true. And the reason that it's not true is also given by the function such that the f has Fourier transform equals to 1 on the parallel relate. So this is a nice way to estimate the function, or in some sense estimate the oscillation of the function, because on the right hand side there is no oscillation involved anymore. So the Boolean diameter decoupling is for the first example function whose Fourier transform is supported on the paraboloid. And then there is Boolean diameter Guth decoupling, which is for the second example, that is functions with Fourier transform supported on the moment curve. That is t squared t to the n. Again, there is this this thetas are going to be r to the minus 1 over n arcs. This number also depends on the curvature, and as we can see, the range of p is a lot larger because one can sort of imagine the moment curve is a lot more curved in Rn than the paraboloid. And the Boolean diameter Guth decoupling implies the Vinogradov's mean value theorem in number theory, which is about solutions to system of Delafonte equations. Okay, so I think this is a crash course. It's a very sketchy mini lecture on restriction theory. Now let's talk about projection theory, and then we will see like how restriction theory gives us some tools to study projection theorems, and in the end we will come back and see how the tools we developed in projection theory will in turn help us to understand restriction theory better. So if the previous paths are too technical, too much analysis, now we can come back and study balls and tubes again. So the projection theory study the following simple question. If we have a direction in a unit direction, so a unit vector in S1, and pi theta is the orthogonal projection from R2 to R to the line that's parallel to theta. So the question we are interested in is let's say we have a subset of directions, lambda, and we have a set E, that is those set E. And can we find a theta direction in our set lambda such that the projection image of E to the direction theta has large Hausdorff dimension? So we have a set E, and this blue part is the projection image. Or more, so there are a few examples for. So this example is like the Cantor set, and we know that for some of the directions, the projection image should be quite large, and so this is almost one-dimensional if we take this to be like the four-corner Cantor set who has dimension 1. However, there are some other directions, like, for example, this one, then the projection image can be large because it's because they project to so all the 4 points project to the same point. So this has projection image small. That's why we need a lot of directions so that there exists some direction such that the projection image is large, like this one. And this is small, and this one is large. Even such a simple question, this question 1 was only well understood like a couple of years ago. So and more generally, so here this is only about from R2 to R. So more generally, we can ask the following question, the following restricted projection question. Let's say V is an n-dimensional subspace in Rn. Pi V is the orthogonal projection from Rn to V. So the second question is, suppose M is some number between n1 and n-1, and lambda is a subset of the Grassmannian, so the set of m-dimensional subspace in Rn, and E is some nice, like say, compact subset in Rn. Now the question is, can we find an m-dimensional subspace such that the Hausdorff dimension of the projection image to this subspace is large? So when lambda is the entire Grassmannian, there are some classical results by Mastron and also by Faulkner and Mattila says that yes, it preserves the dimensions, or it attains the maximal dimension, which is m. But in general, so when lambda is some subset, even some nice looking subset, the question 2 can be very hard. So for example, the Kakeya conjecture is a special case of question 2, and this lambda is particularly nice looking, although it's still a very difficult problem to think about. So when we want to study question 2, there is one immediate observation is that it depends on the curvature of lambda. So why this is the case? Because if lambda is like flat, then one can easily find some examples such that the projection image is always a point. So that's like not very interesting, and we want to avoid those examples. For instance, suppose V is a direction in R3, and we can take lambda to be all the directions that's normal to V, perpendicular to V, like this circle. And if E is contained in the line that's spanned by V, and for any theta, since it's perpendicular to V, we project to the line spanned by theta, this will only give us a point. So that's why the Hausdorff dimension of the projection image is 0, because the projection image is just one single point. So this is a quite boring example, and we want to come up with some nice assumptions on lambda that's get rid of this example. And so here is super nice assumption on lambda. Maybe it's like too nice. So and we it's like the following restricted projection theorem is as we will see immediately, it's a very how to say, very rigid restriction lambda, and we have a good estimate, but hopefully in the future one can relax this definition of lambda. So now let's talk about what this nice lambda is. So suppose gamma is a non-degenerate curve in Rn. So non-degenerate means that the determinant of their derivatives is non-zero. For example, the previous moment curve is one non-degenerate curve. So I think it's fair to say that one can just look at this moment curve. That's like a very nice example and capture it. And the proof for moment curve is the same as the proof for general non-degenerate curve. So what is lambda? So recall that lambda is a subset of is a set of m-dimensional subspace in Rn. So for any t, we can define m-dimensional subspace as the span of the first m derivatives of gamma. So lambda is just those collection of m-dimensional of m subspace. Since gamma itself has a lot of curvature because it's moment curve, so we can sort of imagine that this collection lambda has also a lot of curvature in the Grassmannian. And again, and then the orthogonal projection is I will just write PT for short. Is the orthogonal projection from Rn to this m-dimensional subspace spanned by the first m derivative of gamma. The theorem we proved is the following. So for any Borel subset of Rn, for the big almost every t in 0, 1 interval, the Hausdorff dimension of the projection image equals to the minimum of the Hausdorff dimension of E and M. So this is the best possible because this is a Lipschitz map. So the Hausdorff dimension cannot increase. And also the Hausdorff dimension cannot be larger than the Hausdorff dimension of the ambient space we project to. So this is optimal. And this theorem itself is proved by Gan, Guo, and myself, but the problem was introduced by Fassler and Opponen in 2013, where they consider the n equals to 3 case. They had some very nice conjecture. And then later, there is, in recent few years, there is progress by Pramanik, Yang, and Zhao, and using Wolff's method on circle curve tangencies. And there is also, prior to our result, there is also a 6th author paper for the dimension n equals to 3 case. As one can guess, since a key example is the moment curve, the proof uses Bogan-Demeter-Guth decoupling, so to make use of the curvature of gamma. And also so there are two most important ingredients in this proof. One is the use of Bogan-Demeter-Guth decoupling, and the other one is this high-low method in Fourier analysis that we developed in the past 5-6 years. So it's the combination of the two. So this is one example how restriction theory enters this projection problem in geometric measure theory. And And this kind of projections, this particular projection appears naturally. So although this is some sort of coincidence, because when we proved this projection theorems, we had no idea that it could have application. We just thought, okay, cool, we have the techniques we need to generalize the fastener opponent conjecture. So we were just going to prove it. But it turns out that it is closely connected to homogeneous dynamics, and it has applications to homogeneous dynamics and number theory. So one can check the work of Lyndon Strauss, Mohammadi, Wang, and Yang. Their work on effective Oppenheim conjecture. And also they are they're proving some effective other effective conjectures, also not conjecture, effective theorems in homogeneous dynamics that uses some projection theorem results. So maybe let me pause and see if there are any questions, because we are going to move on to another topic later. Okay, so maybe just little remark. Here, as we can see that this lambda is a very restricted set of M space, is given by, say, M, the first M derivatives of a fixed non-generic curve. It's very rigid, so it's natural to ask the following. If one replace those derivatives by some other, let's say, polynomial curves, that's let's say generic, so that we don't have obvious counterexamples, does this still hold? It's not clear at all, and also I think the same method using decoupling would not work, or at least I don't know how to prove the relevant decoupling theorem to make it work. So this is an example of, like, even if we move away from those things we can prove a little bit, it can get quite complicated. Okay. So what we have done previously is say that we add some very rigid curvature assumption on the set of M spaces in Rn. So this, I think one is fair to say that this lambda has a lot of curvature, is a curve with a lot of curvature in the Grassmannian. And now suppose this lambda lacks curvature. And so there will be some obstructions, as we'll see for the Kakeya problem. But if E is away from obstructions, so let's say the set we are projecting, we impose that it can be concentrated on the obstructions that's created by the fact that lambda lacks curvature. Do we still want to have a good estimate on the projection image? And how do we add assumptions on those E depending on the obstructions? Are there any questions?
Yes, there is one.
Yes, if you let go the restriction on curvature, then instead of the Grassmannian, would one be working with the Chow variety, which parametrizes manifolds, submanifolds of given dimension?
Parameterize what manifold in a given dimension?
Yes, it's for algebraic algebraic manifolds in Rn. And it parametrizes instead of parametrizes the linear subspaces, it parametrizes manifolds.
Wow. So do you mean project to manifold instead of projecting?
Yeah, and then project in the same way.
I have never thought about it and how to define a projection to a manifold instead of a linear subspace.
I don't know. It's you have the same problem here for projection to if you let go of the restriction on curvature. How do you define the projection?
That's a good question. So I know there's people also study nonlinear projections, so it's not necessarily project to subspace. So it's like instead of, let's say, orthogonal projection, one can replace the orthogonal projection by some nonlinear maps. Maybe some of them can be translated in what you mean by project to some manifold.
Mm-hmm. Thank you.
Mm-hmm. Yeah, thanks for the very nice question. So yeah, so let's talk about the next topic. Again, we understand a little bit, but it's if we move away from the problem that we can understand, it becomes very difficult again. So let's see. So before going to before talking about Kakeya, and let's just talk about one simple example and to help us to understand what it means when E is away from obstructions. So previously, we have this example, like suppose we have a given direction in R3, so V, and then lambda is all the directions that is perpendicular to V. So lambda lies on this two plane intersecting the unit sphere. And what is the obstruction that we have seen before? So previously, the obstruction is, so this is the line parallel to theta, and this is the direction of V. And we said that previously, if our set E is containing one of those lines, then the projection image will just be one point. So this is pretty boring. And like by saying E has to be away from obstructions, we can just say, okay, E shouldn't be concentrated on any of those perpendicular lines. For instance, when E is like this, then one can show that there exists a direction such that the projection image has dimension greater than half of dimension of E. So I'm not being very quantitative here, but just sort of how to say illustrate by picture. So if E is like this, then it's concentrated on obstruction, and if E is not concentrated on one line, but something like this, then we expect it to have large dimension. So that's the spirit of how we are going to add assumption on E and how we expect to prove better estimate. Now let's talk about how to rephrase the Kakeya conjecture as a special case of observation 2. So the point is, this rephrase is that as we will see very soon, the lambda that's defined the Kakeya conjecture is a very special curve on the Grassmannian, but there may be other curves that looks like this special curve. So it's natural to ask that if we impose some similar condition on E, do we still have the same projection bound? So it's not clear yet, but it feels to me that this is a quite natural question to ask and see if we can generalize our result. So let me just rephrase the Kakeya conjecture in terms of the restricted projection. So it's not hard. So first of all, a typical line in Rn can be parameterized by a point in R2n-1. So suppose we have two vectors A and B in n-1 dimensional. So we can define a line in N by LAB, that is, this line hit the horizontal plane at the point A0, and it has direction B1. So that is the line. And so what is the set that we are projecting? E is the set of parameters for our lines, right? So if we define the projection pi2 as this AB project to B, remember B defines the direction of the line. So pi2E equals to the unit cube, just means that we have a line in every direction, more or less, after maybe taking constant copies of that. So this condition is the same as we have a line in every direction. And E, recall that E is the parameter space. It's the set that parameterize our set of line segments in the Kakeya set. So then K equals to union of the unit line segment LAB is a Kakeya set in Rn. So that's the relation. So this is a Kakeya set, and this E is the object that we are going to do restricted projection from R2n-1 to Rn-1. And what is lambda? Is everything can be written out in parameters. So lambda is the set of a curve in the Grassmannian that is n-1 dimensional subspace in R2n-1 is the curve defined by lambda is vt. Each vt is the span of the following vector 1, 0, 0. So that's the first n-1 coordinate, and then t 0, 0, 0, and similarly 0, 1. So this is vt. So it's quite simple because the projection, the orthogonal projection from R2n-1 to Rn-1 is just A, comma B maps to A plus BT. So yeah, you can, just these two things are equivalent. I think it's much easier to remember this than anything else. Also is because how are they related? Recall that a line is this A0 and B1t. So this just tells you what are the first n-1 coordinate. The last coordinate is t on this line, and the first n-1 coordinate is A plus BT. So the Kakeya set conjecture says that the Hausdorff dimension of the Kakeya set equals to n. This is equivalent as saying that suppose E is a subset of 2n-1, and the projection to the last n-1 coordinate is the unit cube. Then for almost every t in 0, 1, the Hausdorff dimension of the projection image is n-1 dimension. So what it says is also quite simple. So we have a set of lines, and the union is the Kakeya set. And what is PTE? So PTE just tells us that if we slice the union of lines at height t, so we get a point, we get some subset of n-1 on this horizontal hyperplane of height t, then it just says that by Fubini, if we integrate on the height, get dimension n, then for a typical horizontal slice, we should have dimension n-1. So that is what it means. And this assumption is just one assumption that tells us that E should be away from obstructions. So if we don't have this assumption, then there is this simple obstruction. For example, when n equals to 3, we can take E to be like A0, B0, and AB in 0, 1. So the obstructions, if we translate back to the line problem, It just says that we can take a lot of lines, a lot of coplanar lines, then its union cannot have large dimension because the union is stuck in a plane. So this is a natural obstruction, and what one can rephrase the Kakeya conjecture says that if we have one line in every direction, then it is then obviously it's away from any of those obstructions, and this is so this is just one assumption that tells us that E is away from obstructions, but it's not clear that it is the natural assumption. And this is indeed what Josh and I proved. So so far it's only in dimension 3. In higher dimension there are other difficulty, but in dimension 3 what we proved can be rephrased as follows. If E is not concentrated on obstructions, then for almost every T, the projection image has we have the optimal estimate. The Hausdorff dimension for the projection image is the minimum of the Hausdorff dimension of E and 2. And that's as we said, this is the best possible. And so when our Wolf axioms and the assumptions we add that Josh and I talked about in previous lectures can be translated to the same assumption saying that E is not concentrated on obstructions. And so here comes a natural question. So this is a very particular curve that has obstructions. Even from R4 to R2, if we consider other curves that also have obstructions, can we somehow translate this condition on the Kakeya curve, the map, this lambda, to other similar setting and still have the same bound? So that's a very natural next question to think about. And there are some, again, open problems that that I think it's quite nice to think about, and it's not clear at all how to do it. So first question is give a criteria. So one can still consider this restricted, very special Kakeya type restricted projection in higher dimensions. Can we give a criterion on E such that we have this optimal projection bound? And if we can have a nice criterion, this would imply the Kakeya conjecture in Rn. But maybe in order to prove this conjecture in Rn, we need to come up with the right criterion and prove something stronger as what we did in R3 case. And similarly, let's just consider very simple problem from R4 to R2. Suppose we have two, let's say, polynomial curves. Can we give a criterion on those polynomial curves such that we have the optimal projection theorem with no assumption of E? So I guess I will end here. Thank you very much for your attention.
Thank you very much, Wang. Are there any questions in the room or online? Is a question? Yes, there is one. Yeah.
Hello, thank you for the presentation. Do you have any ideas for the criterion on E for the first open question? So there is one for dimension 3, if I understand, and for general dimension, do you have any ideas for a relevant criterion, or have you tried some criterions that did not work? Yeah.
I mean, again, this, if we translate back to, because as we said, this is the same as union of lines probably in Rn. I think, yes, there are some that we could conjecture some criteria. And in fact, this was, I think Josh was the one who told me the right thing to think about. Let's say when n is greater or equal than 4. So let's talk about line. Union of line problem that can be translated. So one needs to get rid of the following on x, y minus z, w equals to 1. So it means that the lines are this contains many lines in R4. And it's an algebraic variety. And so it has dimension 3 instead of 4. So this is another type of example. This is another type of obstruction that we need to get rid of. So it's natural to conjecture that. So previously, the obstruction in R3 is just some variance of like plane slab. We can take all the convex set. And here in higher dimension, it's not the necessary condition. It says that those lines cannot be concentrated on any semi-algebraic sets. So one can translate convert this semi-algebraic set condition to a criterion on E, and this can be translated. But maybe this is also sufficient, but it needs to be proved, and I'm not sure yet.
If not, let's thank again Wang for her very nice lecture.
Thank you very much.
And Hong, we hope that you will be able to come to Montreal in the future at another time. Thank you so much.
Yeah, I would love to visit. Thank you. Thank you very much.
Thank you.